Good day, everyone. We are the Group 2, and our members are Manigsaca Francthene, Navaluna Christopher, and Tantoy Jasonry. We're here to discuss about the understanding about the maritime sextant. Before we're going to dig deeper with our topic, we're here to present our objectives or our intended learning outcome. Next slide. So these are our intended learning outcomes. At the end of this report, student may be able to know the errors of sextant, to know the pointers use of the sextant, and to know how to care and do maintenance on a sextant. Next slide. Errors of the sextant. So the errors of the sextant can be classified into two, which are the adjustable errors, adjustable on board, and non-adjustable errors, not adjustable on board. So by the name itself, understandable siya nga the adjustable errors can be adjust on board, and the non-adjustable errors are errors that cannot be adjust on board. So next. So these are the examples of the adjustable errors of the sextant. First is the error of perpendicularity. So what is error of perpendicularity? This is caused when the index glass is not perpendicular to the plane of the instrument. So ang index glass part na siya or kanang part na siya sa sextant nga makita nato nga na video nga i-present later on nga di siya perpendicular sa plane of the instrument. So how to check this error? So first, to clamp the index bar about the middle of the arc, hold the sextant horizontally. With the arc away from you, look obliquely into the index mirror till the arc of the sextant and its reflection in the index mirror are seen simultaneously. If in alignment, the error does not exist. If not, turn the adjustment screw at the back of the index glass until they are aligned. So nare adjustment screw nga nimo i-use to adjust the mirrors or the index mirror so that they will be aligned. Next. Next slide. Next will be the side error. So what is side error? These are error caused by the horizon glass not being perpendicular to the plane of the instrument. So kanang horizon glass part kay siya sa sextant same as sa katong index. So how to check this error? First, you'll clamp the index bar at a 0 degree. So hold the sextant vertically and look at the heavenly body. So katong before, katong perpendicular kay horizontally, kani vertically ni siya. So turn the micrometer one way and then the other while looking at the body. The reflected image of the body will move above and directly below the image and should pass exactly over it. If the reflected image passes through the left or the right direct image, side error exists. This error can be removed by turning the adjustment screw until the true and reflected horizon appears in the same line. So from the di nato makita nga kanang properly adjust na ang kanang side error if ma-align na ang true and reflective horizons. Next slide. And next will be the index error. So index error. This is caused if the index mirror and the horizon glass, so mao ni na-involve naton duha katong side error o katong error of perpendicularity are not exactly parallel to each other. So when the index is set at 0 degree, so basically this is the difference between the optical zero of the sextant and its graduated zero. So term off the arc if the optical zero lies to the right of the graduated zero, and turned on the arc if the optical zero lies to the left of the graduated zero. There are methods of obtaining the index error of a sextant. So further explain na siya sa kanang video sa makikita sa mga report. So A, by observing the horizon, and B, by observing the star of the planet. So A, you need to clamp the index at 0 degree. So mao gina ang 0 degree. So this is the neutral degree. Good. Gamit nimo sa pag-adjust sa imong sextant. Holding the sextant vertically, looking at the horizon. The reflected image and the directed image should appear in a perfect line. So ma-align gud siya gyapon, same as sa atong side error. If not, turn the micrometer until they coincide exactly. The reading of the micrometer on or off the arc gives the IE. So the B is where you clamp the index at the 0 or neutral degree, holding the sextant vertically, looking at the star and the planets. So imong i-base ani sa imong pag imong base ani pag correct sa error kay ang mga heavenly bodies, which is the star, the planet, etc. Next will be the reflected and direct image must coincide. If not, turn the micrometer till they do. The reading of the micrometer on or off the arc gives the IE. So ma-sure na ginato if kanang sakto na ang pag-adjust sa sextant, inig ka align sa katong mga mirrors. So next, by A, B, and C. So this is the last this is the last method, which is the by observing the sun. So it still involves heavenly bodies. So set the index at about 32 on the arc. Hold sextant vertically and look at the sun using these shades. So ang kaning shades kay nani sa mga different types, kanang different thickness sa shades nga mo gamiton para dili madaot imong eyes sinikat tanaw nimo directly sa sun ato. Turn the micrometer until their closer limbs just touch note reading on. And set the index about 32 of the arc and look at the sun. The reflected image of the sun will appear above the direct image. And turn the micrometer until their closer limbs just touch. Note reading off the arc. The name of IE is the name of the reading having a higher numerical value. So this will be further discussed by our group mate, which is Christopher Navaluna. So
Thank you, Minister Manigsaca. So let's go to the next error of the adjustable error, which is the error of collimation. So this error collimation is due to the axis of the telescope that not being parallel to the plane of the instrument, or the telescope is not attached to the sextant in such manner that it cannot tilt. So these kanang modern sextants are therefore not provided with any collimating screw. So actually guys, ang ganing error of collimation kay nanani siya sa kanang not adjustable ba, non-adjustable din siya ma-adjust, pero for kaning sa una na sextant kay giapil ang error of collimation sa adjustable. So unsa man siya, unsa man na error? So this is error of course if the telescope is not parallel to the frame of the sextant. So mo occur sa guys kanang mas less ni siya frequent, kanang di siya frequently mo occur ni kanang compare sa other errors, but when they occur higher than the normal sextant altitude are measured. So to confirm that the telescope is parallel to the frame, set the sextant on the stable table and sight along the frame of the instrument toward the wall. So mana siya guys how to correctly error of collimation. So next slide please. So non-adjustable error of sextant. So as what Mr. Manigsaca said na this non-adjustable error of sextant kay mo ni katong dili ma-adjust, di ba? Watay di na to ma-adjust on board. Not adjustable on board. So nanan siya 5 ka errors, namely the graduation error, centering error, shade error, optical error, and wear on the rock and worm. So graduation error is due to the inaccurate graduation of the main scale on the arc of the micrometer and vernier. Then center vernier cause if the pivot of the index bar is not situated at the geometric center of the arc. So this can cause due to the manufacturing defect or due to the careless handling. So actually guys, kaning mga error kay kanang manufacturing defect yun siya. What mabuhat kanina error. We cannot adjust this. And next is shade error. So the shades should be mounted that their glass surface are normal to the rays of light passing through them, and if not, the distortion will result. The greater number of shade used, the greater the chances of distortion. So next is optical error caused by the prismatic error of the mirrors or aberration in the telescope lens. So mamara siya sa shade error pero caused lang siya sa prismatic errors of mirror. Next is the wear of the rock and worm. So this caused a backlash leading to the inconsistent error. Wearing down of the worm can be due to the lack of lubrication and presence of dust particles and careless handling. So kaning where rock and worm kay this is due to the lack of kanang lubrication or kanang pampa slide sa mga parts sa sextant. So next slide please. So deep. So deep is the angle at the observer between the plane of the observer's sensible horizon and the direction to his visible horizon. So deep occurs because of the observer is not at sea level, and the value of the deep increases as the height of the eye observer increases. So sa may pasabot ani guys. So in short, deep is a correction has to be made to the sextant altitude to allow the for the height of the observer's eye above the horizon. So for example guys, nagbarog ka sa isa ka barko, then nag-sight ka sa isa ka star. So let put the kanang the horizon observer's position on the earth surface kay mato ang O, and E is the position of the eye, imong eye. So if you can see the kanang observer's height level katong mata ba, mata na sa isa ka star, di ba ang angle gikan sa katong kanang horizon padung si star and the height kana at angle sa eye padung sa star kay lahi man. Ang visible horizon deep below the true horizon or the altitude measured sa E or si kaning mata padung sa katong na star kay greater than the measured sa O. So mo na nahitabo nanay deep. So kaning deep moto as what I said na sa correction has to be made to the sextant altitude to allow the height of the observer eye to the horizon. So next slide please.
All right, so I will be the next reporter for today. And by the way, this is Cadet Tantoy Jason Ray. I will be reporting about the pointers on the use of sextant. So before you are going to use sextant, here are some pointers that we need to know, that we need to put in our mind so that we can perfectly or smoothly use the sextant. All right. So first is always check the errors before you use. If you just listen to Mr. Manigsaca and Mr. Navaluna's report, they stated all the errors that is possible in the sextant. So we need to check that one first before we use, so that we can get the absolute direction that or position that we need. All right. So the second one is focus the telescope while looking at the horizon and make a mark on the circumference of the stem. No? So number three is during use, hold the sextant steady. So you cannot use the sextant like you are very kuruke ka. So you need to make it stable so that makuha dyan mo ang perfect position. Alright? So for this, stand with feet slightly apart for balance with hands holding the sextant steady. So in order for you to be steady, no, so you need to put your feet apart nga kanang sakto ra, kay you cannot be balanced when your feet is very far from each other, no, and you cannot do balance when your feet are so close to each other, no. So number four is while observing the altitude of the celestial body, remember to swing the sextant to the other side. The body will appear to move along the arc. Measure altitude at the lowest point on this arc. All right. So, and also, number five is stand as close as far as practicable to the center line of the ship. All right. So, if wala pa man mi kasakay barko, pero as we can see on the video and picture, there are some part of the ship outside the bridge that is center line of the ship. So that is the perfect spot to on where can we use the sextant. All right. So number six is use appropriate dark shades while observing the sun. So as we all know, there are different shades of in the sextant, and there are also kanang different kanang lahi-lahi og kainiton og lahi-lahi og maka-affect sa ang sun sa initanaw nato sa sun. So if ever whenever we use the sextant, we need to use the correct shades as para dili maapektuhan atong mata. All right? So Also, number 7 is if blockish error exists, remember to rotate the micrometer in one direction only. Number 8 is altitudes of stars and planets should be taken during twilight. And number 9 is nighttime sextant observation should be avoided so far as practicable. So since sextant is very accurate when we are going to use it in the horizon and angle to the sun, if possible, we should avoid using it by nighttime because the strong moonlight gives the illusion of a good horizon, which is most probably false ang makuha na to nga position na to. All right. So number 10 is while observing the HSA, set the index at 0. Look at the object on the right through the telescope. Gradually swing the index around and finish while facing the object on the left. Okay, so number 11 is when measuring VSA, look at the top of the object. Set the index at 0 and look at the top of the object. No, VSA is equals to height of the object in meters then, no? So 1852 1852 multiply to ton VSA. All right, so next slide. Okay, so we are not just using sextant in one time only. So all we need to do is to um, do a maintenance and care. All right. So the next topic for today is care and maintenance of sextant. So first is we should not put much stress on the index bar when grasping a sextant. No. So and also never touch the arc. It will smear it. These aren't alovic pair. See. Okay. So number 3 is ensure that worm and rock are clean. So okay. And number 4 is coat worm and rock with Vaseline when not using it for a long time. All right. So the purpose of this one is so that dili siya maabugan. We all know that daghan kay anywhere is daghan yung mga abog-abog. Most of the time samot na ibutan nato sa cabinet, itago na to, no? So that is the importance of that one. So mirrors, lenses, and shades should be wiped clean with a soft cloth. So why? No, why we need to use soft cloth? Because sensitive kay na ang glass and lenses sextant. So whenever we use a rough cloth, it will damage the lenses, like mahanap na siya, something like that. So we need to use the soft cloth para smooth and mas mo clear siya if ever we use it. All right. So 6 is after each use, gently wipe the index mirror horizon glass. This is just the same for number 5 and number 7. Put it in the box when not using it. All right. Just like what I've said, Janina. After you clean it, you just need to put it in a box. I believe all the sextants have their own boxes so that it will be put safely sa bridge sa barko. No, there is a perfect place for the sextant. Okay, but that is one of the very important what we call this the tool in getting the position of the ship. All right. So number 9 is avoid exposure to the sunlight. So whenever we use it, kay magamit mo na ito sa mag-igo mo na sa sun. Pero ang gipasabot ani kay we should not expose the what we call this the sextant when ato na siya i-keep, di na to siya paiguan og sun. All right. So number 10 is keep sextant stowed away from the direct sunlight, dampness, heaters, or blowers. So this means that sextant cannot be dili pwede mainitan if imo lang itago, and also dili siya pwede so sa dampness, heaters, and blowers, no? And all right, if you are still if you have still questions about it, the next we will be showing you a video about sextant. All right.
If you watched the first video, you'll already know the principles behind the sextant and be able to label all the different parts. If you haven't already seen it, I'd advise going back and watching it first. This video we're going to move on and examine errors of a sextant and methods of correction. There are actually many different errors possible on a sextant. We can split them into two different groups, correctable and non-correctable. One error, collimation, actually used to be correctable, but on modern sextants it's more usual for it to be non-correctable nowadays. Let's start by looking at the non-correctable errors. We'll just go through quickly as you can't correct for them anyway. Centering error, this is when the pivot point of the index arm is not perfectly aligned with the centre of the instrument. Prismatic error is when the two planes of the mirrors or glass planes are not parallel to each other. Shade error is the same thing, but it's for the shades, and it causes a slight deflection in the ray of light as it passes through the glass pane. Graduation error is to do with inaccuracies in the graduations of the scale, the vernier, or the micrometer drum. Worm and rack is effectively the wearing of the cogs that control the fine movement of the index arm. And collimation error, this is that one that was correctable on older sextants. It's caused when the axis of the telescope is not perfectly perpendicular to the plane of the instrument. Nowadays the telescope is normally rigidly fixed to the frame, so it's not actually possible to correct. And finally we've got instrument error. This is actually just a total of all the non-correctable errors that we've already discussed. It gives the user an easy way to apply all those manufacturing errors to their readings. Sextants come with a calibration card which gives this instrument error. In theory the error should be negligible, but you can see from this example card that as the sextant reaches its extreme setting, you do need to take account of the instrument error. Now we can move on to the correctable errors. For the correctable errors you need to correct them in the right order. First you've got the error of perpendicularity. This describes the error caused when the index mirror is not perpendicular to the plane of the instrument. To check for perpendicularity error, you set the index arm part way, say 30-40 degrees, and then you look straight across the plane of the instrument so that you can see the arc both directly and reflected in the index mirror. You're looking for the real and reflected arcs to appear continuous and flat. As you can see, this mirror is set perfectly, and that's just because it's a computer-generated model. As I introduce some perpendicularity error, you can see the change in the view. The arc no longer appears continuous. There's a visible step between the two. To correct this error, you just use the adjustment screw. One useful tip for the adjustment screws in my method of correction is that you'll always be adjusting the screw that is at the top of the mirror in relation to the way you are holding the sextant. As you have to hold the sextant on its side to see this error, the screw on the side of the index mirror appears on top, so that's the one that you adjust. All you need to do is turn it one way or the other until the real and reflected views of the arc appear in a straight line. Once they do, you know that the index mirror is perpendicular to the plane of the instrument and is correct. Next, we're going to move on to side error. This is similar to the last error that we looked at, but it's for the horizon mirror instead. So side error is when the horizon mirror is not perpendicular to the plane of the instrument. You can spot side error when the instrument is set at 0 and you look at an object in the distance. If the real object and the reflected object are separated, side error is present. You'll notice the correction screws on the horizon mirror are not the same as those on the index mirror. The screws on the horizon mirror actually correct for both side error and index error. We're going to need to correct for both at the same time. So, what's index error then? Index error is when the index mirror and the horizon mirror are not parallel to each other when the instrument is set at 0. If you set the instrument to 0 and look through the telescope at the horizon, you can spot any index error. If there's a step in the horizon, index error is present. This is why index error and side error need to be corrected together. If you have a sextant with both errors present, images in the telescope will be displaced both horizontally and vertically. The horizontal displacement is due to the side error, and the vertical displacement is due to the index error. Now, everyone has their own way of correcting for these. For me, the simplest way is to just use the horizon. My reasoning is that for almost all sites, you're going to need the horizon anyway, so it should be visible, and it's obvious and easy to find. So, I start by setting the instrument to 0. I want everything to be lined up perfectly when the instrument is set at 0. Then you can just look down the telescope straight at the horizon. You remember we already did this to check for index error. It doesn't really matter at this point if index error is present or not, because as we adjust for side error, we're going to change the index error anyway. At this angle you can't tell about side error, because it's not possible to tell if there is a horizontal displacement. You could rotate the sextant by 90 degrees, which would effectively give you a vertical line to tell you about side error, but that's not actually necessary. All you need to do is to tilt your head slightly, and any side error will show itself with the real and reflected horizons moving apart. Obviously, if you've got a lot of index error to start with, it's harder, so you may have to tilt your head over to 90 degrees, so that all of the error that's visible is side error and none of it is index error. Normally a 45-degree head tilt will be plenty. From this position, you just adjust the screw that is furthest from the frame. I tilt my head to the right, so this screw is now on top. Just turn it one way or the other until the horizon forms a continuous line again. As you bring the sextant back to its normal angle, the horizons may separate again. If they do, this is now due to the index error. Again, you adjust the screw that is on the top. This time it is the one that is nearest the frame. Turn one way or the other until the horizon is again continuous. Then you return to your tilted head position to check whether you've introduced more side error. If so, you can correct for that again. Now you repeat this process a few times until you've eliminated both side error and index error. You may get to a point where you can't eliminate both. If you find that you're just going back and forth between the two positions, you've taken out as much error as it's possible to remove. From here, just make sure your side error is eliminated. Then, any residual index error will have to be removed mathematically. You effectively measure that final little bit of index error by using the micrometer drum to make the horizon continuous. Then, any measurements you take will need to have that index error applied to them. If the error is measured on the arc, you label it on the arc, and it needs to be subtracted from all the measurements to make them true. Likewise, if the error is off the arc, you label it such, and it needs to be added to all measurements to make them true. So theoretically you've now got a sextant with all errors eliminated and are ready to start taking sights. In the next video, I'm going to show you how.
Right, so I think that is all for our report. I hope you enjoyed the video and you get something from us also. And thank you guys for listening. Goodbye.